Hey, good morning. Let's take a look at homework 12.2, acids, bases, and titrations. It's due tonight, so if you haven't done it yet, this hopefully makes things a little bit easier. Get some practice doing the equations and solving a titration. So let me share my document cam with you. Here is the homework. So 20 milliliters of sodium hydroxide is neutralized by 17.4 milliliters of phosphoric acid. So they want to know, what is the acid? Phosphoric acid has the ick at the end, no hydro in front. So that means we're looking for 8, phosphate. I ate something icky. So phosphate, if it ends in ATE, that means we're looking on the back of the periodic table. And there it is, phosphate, PO4 with a -3 charge. So our acid is H3PO4. 3 H's to cancel out that -3 charge. And then should always put aqueous, just because acids, they have to be aqueous. They're not an acid unless they're dissolved in water. How about the base? Well, that's our sodium hydroxide. Again, something that gives off hydroxide ions is our base. So sodium hydroxide, NaOH, there's our base, sodium hydroxide. Again, also probably should put aqueous, not really a base unless it's dissolved in water and it's giving off those OH negatives. All right, question 3, they want to know, write the balanced chemical equation, the complete ionic equation, and the net ionic equation. Let's start off with the balanced chemical equation. We have our base, and again, we don't really have to look up rules. If it's a base, it's going to be dissolved, and it's going to react with our acid to produce, and it's a double replacement. So the 2 positives switch places. We're going to produce water. We know that that's a liquid, and sodium, this positive, now comes over here with the phosphate. Phosphate has a -3 charge. Sodium, he's an alkali metal, so he has a +1 charge. We're going to need 3 sodiums to cancel out that phosphate. 3 of these +1s to cancel out that negatively charged phosphate. Let's find a rule real quick for sodium phosphate. Group 1A, alkali metals, that's sodium. We just mentioned it. Sodium's in that first group. They are soluble. They are soluble. So aqueous. Couldn't quite fit it on the edge of the page there, but put it right there. So this one is soluble. Now we need to balance. Always got to make sure we're balanced. So 1 sodium on this side. We've got 3 sodiums on this side. So I'll need to put a 3 out in front of my sodium. How about H3PO4? I've got 3 H's. Only 1 H, we'll put a 3 there. Hey, that works out for my OH. I kind of skipped my hydroxide ion. Now I've got 3 of each of them. So we are balanced. 1 phosphate, 1 phosphate, we're good. All right, time to move on. The CIE, the complete ionic equation. So this is where we break up all of our aqueous compounds. So sodium hydroxide went into water and it made 3 sodiums, and anytime you have an ion, it has to be aqueous. So I've got 3 sodiums, and the hydroxide ion came off, and all 3 of them, remember I have 3 NaOHs, so that means 3 hydroxide ions. All right, and then my acid also goes into water, and that's going to split apart into its 2 halves, hydrogen and phosphate. And don't pull the P and the O off, they are together as 1 ion. So I have 3 hydrogen ions and just 1 phosphate ion, PO4, -3. All right, so there's my reactant side. That's this side. Now I have to do the product side over here. So put an arrow. The water is liquid. We don't split that up. Anything that's not aqueous, that stays together. So 3HOH as liquid, and my sodium phosphate, that does get split up. That one is aqueous, so I'm going to end up with 3 sodiums and 1 phosphate. Again, that 3 only applies to the sodium, not the phosphate. So there we go. There is my complete ionic equation. The next step, our net ionic equation, we want to eliminate all of our spectator ions. Who doesn't react? Who is the same on both sides? Let's start with sodium. Yeah, he's the same. He's 3Na plus aqueous and 3Na plus aqueous. So we're not going to write him. How about hydroxide? 3OH negative. I don't see that on this side. That's because he became a part of water. So yes, he does change. He will be in my net ionic equation. 3 hydrogen ions. Hey, same thing. They joined up with the hydroxides to make water. So they do change. I am going to put them in there. Not the phosphate ion. He doesn't change. He still remains aqueous. So then on my product side, the only thing I have left are my 3 waters. There's my net ionic equation. Moving on to problem number 4, solve for the concentration of sodium hydroxide. All right, so now we're on to the titration part. We have 20 milliliters of sodium hydroxide, and we knew that it took 17.4 milliliters of 1 molar phosphoric acid to neutralize it. So we're solving for concentration, another word for concentration, molarity, we all know that one. So moles of NaOH over liters of NaOH. That's what we're trying to solve for. Again, I'm going to start by getting the easy one out of the way. We're looking for liters of NaOH on the bottom. We have a 20 milliliter solution. I think we can all go from 20 milliliters of NaOH to liters of NaOH. That's a pretty easy conversion there. We should all be pretty familiar with it. And we're halfway home. We've got milliliters of NaOH canceled out. Liters on bottom, that's what we wanted. So there we go, we're halfway home. The next step, all right, I've got 2 numbers left I can work with. Guys, I can't put a double unit here. I can't put moles per liter. I've already got my number on bottom there. So the only number I can work with, and I've been advising you guys stay away from starting with that to begin with, the only one I can work with is that 17.4 milliliters of phosphoric acid. So let's grab that. 17.4 milliliters of phosphoric acid. Put that there. Again, this comes from experience, but you guys are gaining experience every day. When I'm working with molarity, I need liters. So let's convert that milliliters into liters. So milliliters goes on the bottom. There are 1,000 of them in 1 liter. Now that we have liters, we can use that molarity. Again, make sure we put liters on the bottom, and our molarity is 1 mole per liter. So there's our molarity. Let's make sure we get the correct number of digits here. So 1.0 moles of H3PO4. 1.0 moles of H3PO4 per liter of H3PO4. Now we're almost there. We have moles on top. We want moles on top. Unfortunately, we have moles of acid, and we want moles of sodium hydroxide. So one last step. This is where our balanced chemical equation comes into play. 3 moles of sodium hydroxide to 1 mole phosphoric acid. So put the 1 mole of phosphoric acid on the bottom, and that makes 3 moles sodium hydroxide, and voila, our units are canceled out. We have moles sodium hydroxide over liters sodium hydroxide. Everything else at this point should have canceled out. One of the 2 units we want left. Time to crunch number. 17.4 divided by 20.0 times 1,000 divided by 1,000 times 1.0 times 3. We end up with 2.61. That's a pretty strong base. 2.61 molar NaOH. Let's just double check our significant digits here. We've got 3 there, 3 there. These are infinite values. Oh, hey, our molarity of acid only has 2 significant digits. So I need to erase that 1. Not enough to round that 6 up to a 7. So we only want 2 significant digits because that 1.0. So our final answer, 2.6 molar NaOH. All right, guys, that's how we do a titration. The complete ionic and net ionic equations, identifying acids and bases. You have another very similar homework to do tonight. So I'll let you guys get on that now. Have a great weekend, and I'll see you next week, just before spring break.